Today we're going to be discussing Gauss's law. This is one of 4 of Maxwell's equations which describe electromagnetism. And Gauss's law is particularly powerful for solving electrostatic problems. For example, let's suppose we have a charge density, ρ. Well, we know that this charge density produces some sort of electric field, E, as you can see in our little example here. Gauss's law actually has 2 forms, and you're probably most familiar with its differential form, which you can read here. What it does is it relates the divergence of the electric field E with the charge density divided by a constant of proportionality, which is known as epsilon naught. So this differential form of Gauss's law is extremely powerful if you already know the electric field, and you want to know the charge distribution. But what if, instead, you know something about the charge density, and instead you want to know something about the electric field? Well, fortunately, we can transform Gauss's law from differential to integral form, and this will give us exactly what we want. So how do we do this? What we're going to have to do is introduce a concept known as a boundary surface. This is any closed surface which we can draw around our charge distribution. So for example, let's take the charge distribution up here, and let's draw a sphere around it. So if you can imagine a spherical shell surrounding our charge distribution. So it doesn't have to be a sphere, it could be a cylinder, it could be a cone. It just simply has to be any closed boundary which encapsulates ρ. So let's give a name for our little boundary surface here. We're going to call it S. And we're going to call the volume enclosed by this boundary surface as V. With this definition of a boundary surface, we can now transform Gauss's law. To do so, we're going to take the integral over the volume enclosed within S, that's V, on both sides of this equation. So what does this look like? Well, we're going to take a volume integral over grad dot E, where dV here is our infinitesimal volume unit. And we're going to equate that to the volume integral over ρ divided by epsilon naught, also multiplied by dV. So let's focus on the right-hand side of this equation first. Well, if I have a charge distribution, and I add up every little piece of this charge distribution within a volume, what am I left with? That's simply the total charge enclosed within that volume. So let's call that Q. And it's still going to be divided by epsilon naught. So that is the total charge within S. But what about the left-hand side of this equation? Well, it's a bit more complicated. Fortunately, we can use a mathematical principle called the divergence theorem to simplify it greatly. We're not going to go into all of the mathematical details here, but in principle, it allows us to change this volume integral of the divergence of E into a surface integral over E itself. So how does this work? In essence, it allows us to write a surface integral of E dot producted with the infinitesimal unit of area on S. So what does this quantity mean? What's its significance? Well, actually, this is commonly denoted as the electric field flux, and it's described usually through the character phi. In particular, it's the electric flux through S. But what does this mean? Well, in essence, it describes the total electric field which is flowing or permeating through S. We've now finished our derivation of the integral form of Gauss's law. It describes the total electric flux phi through S to the total charge Q within S. But how does this help us solve electrostatic problems? Well, let's assume we know the total charge within a system. If there's some sort of symmetry to this charge distribution, for example, it's spherical, we can use the integral form of Gauss's law to calculate the electric field. Alternatively, let's assume that our system has cylindrical symmetry, for example, a charged wire. We can then use the integral form of Gauss's law to calculate the electric field at any point distant from that wire. In summary, we've transformed the differential form of Gauss's law into its integral form. This has opened up new possibilities for us to solve electrostatics problems, depending whether we know something about the electric field or we know something about the charge distribution.